To begin with this review, I would like to suggest that all of you stay calm and composed and alert when you're attempting the questions on the exam. Okay. Um, we are going to test you, but we are not going to tease and test you. So just when you're answering your questions, read the question carefully, understand what is being asked, and then answer the question. Don't assume that from the first few words that this is what is being asked. You know, in one of the versions, we might have what is the true sentence, or we could ask for other version, what is the false sentence, or something like that. So make sure that you read the questions completely. All right, with that being said, all of you know when your exam is tomorrow. I will be working on my doc cam, but if you all don't feel that's comfortable, then just let me know. Okay. Okay. So I haven't started writing anything yet. What I will do is I will switch between my paper and the screen if we have to do that. First of all, any questions that you would like me to answer?
I was just wondering if you could like do a H NMR question and then a C NMR, like, and then show like the difference of how we would go about solving.
Okay.
Like,
Okay. Before I answer that question, let's start with a complicated part. And it would be a very good idea if all of you can write along, because you know it'll help you see better. So I have this kind of alkene and I have this reagent. What is my new product going to look like? This is going to have a bridged kind of an effect, right? So my incoming nucleophile is going to come from the opposite side, which is the anti-attack. But my incoming nucleophile, which carbon is it going to attack? The less substituted carbon or the more substituted carbon? My incoming, very good. So my incoming nucleophile is going to attack the more substituted carbon, and hence Markovnikov's rule. Anti-attack, Markovnikov's rule. And so this is the kind of product that I will get eventually on the more substituted carbon. And don't worry, I'm going to come back to your question anyways. But instead of this reagent, if I had used my acetic reagent, what would have happened at that point? Now I cannot control my stereochemistry. So the pi electrons, the rich pi electrons are going to attack this hydrogen. A carbocation will be generated. Why carbocation is on the more substituted and why the hydrogen, the incoming proton, is on the less substituted? This is how Markovnikov's rule will play. This is a secondary carbocation. Every time a carbocation forms, it will rearrange. So it rearranges and forms tertiary carbocation. So if you can, and if you wanted rearrangements, you should use this particular reagent. However, if you wanted No rearrangements, but still Markovnikov's rule. So this still followed the Markovnikov's rule. Could you control the stereochemistry? You cannot control the stereochemistry because now the carbocation is a flat structure, sp2 hybridized carbon. The OH can attack from the top, the OH can attack from the bottom. You are going to get mixed or a racemic mixture of this product. Both of these are CH3s, so this is not a chiral compound. But coming back to your question, how many hydrogen NMR peaks will I see in this structure? Can anybody guess?
3
Okay, so
or
both
4 actually.
both of these CH3s are same, right? And then this carbon with 3 hydrogens is different from these CH3s.
I thought it would be like for A, because on the same side they have the CH3, but on the opposite has OH, and then it's different for the bottom.
Very good. And the conformation takes care of that. So it keeps rotating across this single bond. This is not a double bond. When you have a double bond, then absolutely, then it matters because now it is a locked conformation. But when you have a single bond, conformations will occur across this carbon-carbon. So this CH3 is different. These CH3s are different. And then this carbon has 4 bonds. The 4th bond is the hidden hydrogen bond. So this is also going to appear. Moreover, this carbon also has a hydrogen bond. This is going to be different. And then this hydroxyl hydrogen is going to be different as well. Are we good?
Irma?
Yes, please go ahead.
If there was a double bond, would those methyl groups, would those be different?
If your environment is different, then yes. Yes, now they are different. They don't have the same environment.
Okay.
Now I have, based on this, 5 peaks from just hydrogen. In my hydrogen NMR, I just have to look at the hydrogens, the different kinds of hydrogens. Plus, I also have to remember when I'm looking at my hydrogen NMR and I'm looking only at the hydrogen atoms, I don't have to look at the carbon atoms when I'm looking at my protons. Only focus on my hydrogen atoms. Let's look at the carbon NMR now. How many peaks will I get from my carbon NMR? So 1, 2, 3, and 4. Any questions how I got my 4 carbon peaks? Another question that I have for all of you is, what will be the splitting patterns of these hydrogens will be? Okay, that is also something that you must think about. So you definitely need to think about number of peaks. And then you think about the splitting pattern. So looking at these hydrogens, what will be the splitting pattern for these 6 hydrogens be? So I'm going to list them as A, 6 hydrogens. How many neighbors do these 6 hydrogens have? This one little neighbor right here. So when you have one neighbor, what is your splitting pattern? It is a doublet. Remember, number of neighbors plus 1 gives you your splitting or multiplicity. So your number of neighbors for these 6 hydrogens, for these magnetically equivalent hydrogens, there is only one neighbor on the adjacent carbon. So 1 plus 1 is 2, which will give you a doublet. These 6 hydrogens will give you a doublet. Let's look at HC. So there is one hydrogen right here. How many neighbors this hydrogen has? 3 plus 3, 6. And then this one, 7. So on this tertiary carbon, there are 3 other carbons. And on these 3 carbons, in all, you have 7 hydrogens or 7 neighbors. So for this one hydrogen, how many neighbors do you have? 7. 7 plus 1 is 8. So you will have an octet. And you can also write it as a multiplet if you can choose to do that. Let's look at these 3 hydrogens. So how many neighbors do these 3 hydrogens have? Next to this carbon is only one of these carbons, and you have only one hydrogen atom. So for these 3 hydrogens, there is only one neighbor, only one neighbor. 1 plus 1 is 2. So this with 3 hydrogens will also have a doublet. If you look at this particular hydrogen, how many neighbors this hydrogen has? 3 on this carbon, 1 on this carbon. What about this hydrogen on this oxygen? Will we consider that? Will we consider this hydrogen as a neighbor to these hydrogens? We will not. Remember your OH, your NH, and your aldehydes hydrogen. They don't act as neighbors ever. So remember that. So coming back to our structure for HD, how many neighbors do I have? 3 and 1. So 4 neighbors. 4 plus 1 is 5, which gives us a quintet or a pentet. So this is denoting for these many hydrogens, this is the splitting pattern that we see. These many hydrogens, this is the splitting pattern that we see. And the last is the hydroxyl hydrogen. So the hydroxyl hydrogens, they do not act as neighbors. They don't act as neighbors. They don't have any neighbors. They will always appear by themselves and as a singlet. Okay. For carbons, we do not expect you to know the splitting, only for protons. Does anybody want to try how many hydrogens and how many carbon peaks will I get here? The student who asked me this question, did you understand this?
Yes, I understand.
Very good. So how many types of hydrogens do I have here, and hence how many hydrogen peaks will I see here? So both of these are exactly the same methyl groups. So hydrogens on these will be equivalent. There is no space for a hydrogen on this carbon. This carbon already has 4 bonds, 1, 2, 3, 4. So no hydrogen here. What about this? This is A, this will be B, this will be C, and this will be D. Number of hydrogen peaks, 4. Number of carbon peaks, carbon, carbon 1, carbon 2, carbon 3, carbon 4. I will have 4 carbon. So if you look again, starting from the same structure, using different reagents, I get different products. And based on NMR, I can distinguish them also. So if you look at these again, let's compare A, B, C, and D. There are definitely 6 hydrogens here. What is the splitting pattern for these 6 hydrogens? How many neighbors do they have? How many neighbors do they have? They have 0 neighbors. And so what will be the splitting pattern be? N plus 1, 0 plus 1 will be a 1 or singlet. Similarly, if you look at D, 1 hydrogen, that stays as singlet. No neighbor for this guy. For B, 2 hydrogens. How many neighbors this has? 3 neighbors here, 0 neighbors here. So 3 plus 1 is a quartet. How many hydrogens here? 3 hydrogens here. These 3 hydrogens have 2 neighbors, which gives us a triplet. So you can see distinctly how our NMR is differentiated. Okay, so you should be able to figure out your number of peaks. You should be able to figure out your splitting patterns, and you must also be able to guesstimate or do an educated guess of where the chemical shift values of these will appear. Okay, so for that, you will have to look at your NMR handout. Okay, let's look at another.
Dr. Verma,
Go ahead, go ahead.
we were told in Dr. Morgan's class that we won't have the handout for the tests. So we just have to memorize those, don't we?
Yes, the NMR, yes. So
Gotcha.
you don't have to, if you think about it, you should know the, sequence in which we have arranged it. All of your sp3 carbons are upfield. As you place an electronegative group on your molecule, that's how the electronegative group will remove the electrons from the atom, making that atom de-shielded, and your peaks will start to shift downfield. So that is something that you will have to think about. Who can pull more electrons? Who can be more electron withdrawing? Right? So for example, when you are looking here, the carbons next to the oxygen and the hydrogens of these carbons, they are going to be very downfield. They're going to be shifting downfield compared to all the other hydrogens, right? And this hydrogen will be even further downfield because it is directly attached to the oxygen. So whoever pulls the electrons more gets shifted downfield. Did that help, Nelson, or did I confuse you?
That helps. Thank you.
Okay, good. So I'm going to use the same alkene that I was using. And now what is the kind of product that we are going to see? Now you're going to see anti-Markovnikov's rule. What does anti-Markovnikov rule state? It states that the incoming nucleophile will go to the less substituted alkene. So on the alkene, you have the substituted carbon. On the alkene, you have the less substituted carbon. Now, there are 2 hydrogens here and 1 hydrogen here, but only this carbon has some substitutions on it. And if you do the NMR, the number of signals for this structure also, it will be different from the NMR that we did for the other 3. Now, let me take this chance to do this also. Do you all remember what this is, ROR? ROR is nothing but peroxide, right? So you have HBr and you have ROR. If it were just HBr, your Br, the incoming nucleophile, would go to the more substituted carbon. But now you are going to see another anti-Markovnikov's rule. And for your course, these are the only 2 anti-Markovnikov rule generating reagents that will take you or add something on the less substituted carbon. And I wanted to share this question with you because one of the students asked this question to me during office hours today. So I thought I'll share this with all of you. So what is the final product going to be here? Let's try this all together. So the first thing that is going to happen is between this alkene and HBr with peroxide. So remember, this is a peroxide. My Br is going to go to the less substituted carbon, followed by lithium and ether. What does happen when you combine lithium with any alkyl halide? With any alkyl halide and a metal ion like lithium or magnesium, you are going to get a C negative. So this C is going to become a C negative, and an organometallic reagent will be generated. Do you all understand this part? So from this part, I have this, and from this part, I have this. And the next step is the addition of your nucleophile. What is nucleophile? Electron-rich molecule. Your nucleophile is going to attack the electrophilic carbon. The pi bond opens. So this carbon, which already had 4 bonds, now had a 5th group attacking it, which led to the opening of this pi bond. And what will this carbon get? This carbon is going to get this C negative, this C right here, this C right here. So 1, 2, 3. Now we cannot end this right here. There is going to be a resonance. In a allylic pattern, if resonance or spread of electrons can occur, it is going to occur. So these electron-rich oxygen will move towards the lone pair. So one other thing that you always have to remember, negative charges are the strongest electron donors, followed by lone pairs, followed by pi bonds. So among all of them, negative charges are the strongest electron donors. So among a negative charge and a lone pair, negative charge is the stronger electron donor. It will close the pi and bring these electrons to this oxygen. This will generate what? You will again close up on your C single bond. This carbon will keep this ethyl group, while these 1, 2, 3. So 1, 2, 3 groups stay as they would. Any questions so far? No questions? So this particular molecule, there were 2 of these. So 2 of these molecules were also generated. One of the molecules attacked this carbonyl, the other will again be ready to attack this carbonyl. So it will keep attacking it until it completely saturates it. And this happens only when you have an ester functionality, not with a ketone, not with an aldehyde, only with a ester functionality. Do you all remember what an ester looks like? Carbonyl next to a OR group. A ketone or aldehyde would either have R groups or R and a H. Now when this addition occurs, 1, 2, 3, and these 2 are exactly the same things. I just wrote them differently. In the presence of acidic solution, this oxygen will be replaced by the hydrogen. Okay. So I have just rewritten the CH2, CH2, CH3 as this chain format. So this is going to be your final product when you will have a sequence like this. Any questions on this part? So organometallic reagents. So you should know how to create the different Grignard reagents, the different lithium reagents. So how do we know how to form these? This is my R group, this is my R group, this is my R group. I just need Rx. What is X? X is my leaving group. What leaving groups do you know of? Chlorine, bromine, iodine. What about fluorine? Fluorine is a bad leaving group. You have RX, OMS, OTS, OTF. RX plus magnesium in presence of ether is going to give you RMgX. So the magnesium just gets inserted between R and X. On the other hand, if you have R and X with lithium, then you get a lithiated product and you don't have to worry about the bromine. It becomes lithium bromide. But this is right here is your Grignard region, the strong nucleophile. Any carbon negative is going to be very, very strong nucleophile.
Dr. Verma, can you
Yes.
bring the paper back, please?
Yes, yes,
I didn't
yes,
get the bottom
absolutely.
part. Thank you.
Yes, yes.
Okay.
Meanwhile, if you have not, then think about the products that you will form, starting from this substrate using these three different reagents. So what will happen when you react this? What will happen when you will react this? When you will react this individually or separately? Think about it, and that should also give you some more practice. Now for your OH reactions, one of the most important OH reactions is when you will have sulfonated products. And what happens or what kind of products form when you have the phosphorated product? Yeah. So this is also something that you must think about. So what kind of a functional group is this? This is a ester functional group. So if I have a hydrogen here and I have hydrogens here, let me label them A and B. Which of these two will be more downfield? Who can tell me? Take a guess, maybe.
Would hydrogen B be downfield because it's closer to the O?
Exactly. Very good. Because it is directly attached to this oxygen, the hydrogens will be pulled even more severely. They will be more de-shielded. They will be more downfield. Very good, Raven. So let's say I have a setup like this. This is the ester, and this is my ketone. Can you all recognize the ester, the alkene, and the ketone? Can you all recognize that? So what would be the product if I use hydrogenation method? From the same structure, what if I use sodium borohydride followed by acetic solution? And what would be the product if I use lithium aluminum hydride followed by acetic solution? One hint to all of you, these are going to reduce. What does reduce mean? Add hydrogen. They are going to add hydrogen across the pi bonds. How and which ones? This is something that you need to know. So for example, sodium borohydride is a very selective reducing agent. It will only reduce what?
Aldehydes and ketones.
Very good. So sodium borohydride only reduces aldehydes or ketones. They don't reduce alkenes. They never reduce esters. So what is the product that you're going to see here? So the alkene stays, the ester stays, and this carbon right here gets reduced. So instead of having a pi bond with OH, I'm sorry, oxygen, it will now have just a OH and this one hydrogen. What about lithium aluminum hydride? Lithium aluminum hydride is non-selective with carbonyls. All the carbonyl groups will be completely reduced. But what about this double bond right here? Will it be affected or will it stay untouched? It will stay untouched. So let's look at this ketone group with lithium aluminum hydride. This carbon right here, will become your OH. And of course, the hydrogen comes here. This carbon right here will lose its toxic group. But the C double bond O will become OH. So you have a CH2 for this carbon now. This carbon right here gets CH2. What about the alkene? The alkene stays. No, nothing will happen to the alkene. So both your reducing agents, sodium borohydride and lithium aluminum hydride, will not do anything to your alkene. Who will do something to the alkene? When you will have hydrogenation under strong conditions. The only problem with that is now your carbonyl groups will not be affected. This double bond, however, will be reduced. So this carbon had only one hydrogen, this carbon had only one hydrogen. You will add hydrogens. Now they are in all 4 hydrogens. This is not a SN1. This is an addition across the double bond. It happens in a syn fashion. You know, when you have this catalyst and you have this hydrogen. So lithium aluminum hydride is also not SN1. You know, the hydride, it attacks the carbonyl. There are 4 hydrides. And what is a hydride? A H negative. Lithium is a metal, aluminum is a metal. So what that leaves hydrogens to be? They are all negatively charged. Very, very strong base. Usually when you have sodium hydride, that is a base. But this is a strong nucleophile with lithium aluminum hydride. So there are 4 hydrides and all 4 of them can keep attacking this carbonyl until this carbon becomes saturated. Okay, very good. And thanks for that question.
I have a
All right.
question.
Yes, please go ahead.
What with the lithium hydride, what happened to the methyl group?
Which methyl group? This methyl group? This methyl group? That
the other
stays.
one.
That stays. Nothing happens to that.
The one on the other side that was attached.
This OCH3, yes, that leaves.
Oh, okay.
So this carbon now gets rid of this OCH3. And now you just have the H2.
Okay, thank you.
So this attack is actually very similar to what we have seen here. So there was this OR here, and there is this OCH3 here. When the incoming nucleophile attacks this, the pi bond opens. When the incoming hydride attacks this, the pi bond opens. Because there is an allelic situation and resonance occurs, this CO bond gets kicked out. So if I draw this situation again, because of this allelic situation, this pi bond reforms, just like this pi bond was reforming. But in the process, it is kicking the OR group out. Similarly, when this pi bond forms, this kicks out the OR group out. It is usually not easy to break a C single bond O, but it can break only in this allelic pattern or case scenario. Once this happens, this molecule, this hydride, sorry, this hydrogen stays in. And because lithium aluminum hydride is like source of hydrides, it has unending source of hydride, another hydride can come and attack it. You know, so this was my first hydride, this was my second hydride, and you can see both of them right here. Does that answer your question?
Yes, it does. Thank you.
Okay, very good. Now, while we're talking about resonance, let's look at a structure. Let's look at a structure like this. So first of all, do you identify any resonance pattern here? Right, y'all recognize that pattern here? That A, B, C. Now, why did I not go A, B, C? Not with this carbon. What beef do I have with this carbon? And why did I choose this nitrogen? Anybody? What if instead of my positive charge, I had just a simple nitrogen? Nitrogen with a hydrogen. What do you think? Why am I still choosing A, B, C? This as my allelic pattern. This as my allelic pattern. And why am I not including this carbon right here? Can anybody remember why? Because this carbon has nothing to accept, nothing to give away. This positive charge can at least accept electrons. So this carbon right here is just like a wall. You cannot go through that wall. And in this case also, the lone pairs of the nitrogen, they can accommodate the flow of electrons from this direction or this direction. First, let's look at this particular structure. Where will the electrons start from in the allelic pattern? From nitrogen, but nitrogen does not have any lone pairs. It is electron deficient right now. It has given away electrons to make its fourth bond. So it is up to the lone pairs of oxygen. So they are going to move. Like ideally, this would be a bad example. Why? When these electrons come between this, a triple bond may form, which is impossible for this carbon. So this is not allowed. However, the moving electrons can jump to this nitrogen. And so this carbon will still have its 4 bonds because it's going to break one of the pi bonds and make a new bond right here. It can do that. Is this lone pair localized or delocalized? Now let's say that I do form a 5th bond with this nitrogen. This structure is still wrong, right? Nitrogen will never be able to accommodate its 5 bonds on it. So even though it seems like it, there is an allelic pattern involved, and there is an accepting group and a donating group, the resonance will not occur conveniently. But on the other hand, if you look right here, there are lone pairs in this case, and there are lone pairs in this case. Nitrogen, being less electronegative, can give away electrons more easily. And so in this allelic pattern, this is a reasonable resonance to draw. So the nitrogen and carbon make a new bond. When they do that, nitrogen gets a positive charge. Why? Because nitrogen has given away its lone pairs to this double bond. On the other hand, carbon breaks its bond with oxygen, so it can accommodate the 4th incoming bond. And all the electrons are now with oxygen. Now, this is considered as a good resonance or accepted resonance structure, acceptable resonance structure hybrid. Overall charge is neutral. Overall charge is neutral. Okay, so whenever you're making your resonance structures, be very mindful. You cannot just go and jump anywhere. You need to have some form of accepting atom or some form of donating atom there. Now, for example, I have a carbon right here with a negative charge. Now, if I look at it, I can have A, B, C pattern at this, and I can also have A, B, C. I can have both of these. Let's look at oxygen, carbon with the oxygen. Oxygen, carbon with a double bond, oxygen. So instead of an oxygen or a nitrogen, I have just replaced these 2 atoms. That is the only thing that I see here. So redrawing it and writing the resonance structures. Because the lone pairs are more mobile here, one of the resonance structures that you will get is this. And this is just one of the resonance structures. Starting from this, again, now my negative charge is a stronger electron donor. This is going to be my second resonance structure. So you see this? Overall, if you look at all these A, B, C. All of these are acceptable resonance structures. Overall charge is negative. Overall charge is negative. Remember, these two are going to cancel out each other, the plus and the minus. Overall charge is still negative. Out of all of these three, which is going to be the least significant one? The one where you have more charges. That is going to be the least significant one. But the point is, all of you must and should know how to draw out resonance structures.
Can you repeat what you said about the most significant or
About what?
the least significant?
Yes. So when we are looking at the most significant, we don't want any charges on our most significant. So if you look at all the three resonance, and these two are just the same things, right? These two are just the same thing. I just redrew them again to show you the different resonance patterns that can occur on the same structure. But these three, A, B, and C, are resonance hybrid structure of each other. But all of these three are acceptable resonance structures. Out of A, B, and C, C has only one negative charge, A has only one negative charge. If you look at C, the most electronegative element has the negative charge on it, which makes this electronegative group very happy indeed. So among all these three, this particular structure with the negative charge on the electronegative element is the happiest and the most stable of all the three resonance structures that I have. On the other hand, if I look at this structure, how many charges do I see? I see a positive charge, a negative charge right here, a negative charge right here. And overall, if I add up, these two are going to neutralize each other. Overall, I will still have a -1 charge, -1 charge, -1 charge. However, the charge has been split too much. There's so much of splitting in charges. Plus, the oxygen has to accommodate, the electronegative element has to accommodate a positive charge. So this makes this structure unhappy or less stable or less significant. This structure will exist for a fleeting moment compared to C. So C is most stable, will be there for a longer time, followed by A, followed by B. B is going to be the least stable and most insignificant structure that we see. Did that answer your question?
Yes, thank you.
Okay, very good. All right. Now looking at dienes. For your dienes, you primarily have two types of reactions that you have to remember. One of them is when you're adding anything across the diene. And do you all remember how to look at diene? It's a conjugated system. Conjugated means alternated double, single kind of bonds. When you're adding something at low temperature, when you're doing a cold kind of a reaction. So 1, 2, 3, 4, your primary product or your major product would be a 1,2 addition product. It could add across these two alkenes. It could add across these two alkenes also. Okay, so you can have multiple variations of that, but this is going to be your major product. On the other hand, if you have the diene and you're going to add something in the thermodynamic conditions, which is heat. Now you are going to get 1,4 addition product as your major product. Of course, others will form, but this is going to be your major product where your incoming groups will settle here. And why not? If you compare the answer, so let's say I put a bromine here and I put a bromine here also. On the other hand, if I use 1, 2 additions outside the ring, or inside the ring, so you just have to remember at cold conditions, 1, 2 additions will be your major products. Under heat conditions, 1, 4 additions will be your major product. And this is where your Diels-Alder come. So when you're doing your Diels-Alder, there are 2 things that you have to remember. There is a diene and then there is a dienophile. Of course, as the name indicates, the diene must have 2 double bonds. Now, if you look here, both of your structures have 2 double bonds. Which of them is going to be the diene? The diene will have to be in cis orientation. And we also need to have the dienes with electron releasing groups on them. So what are the best electron releasing groups that you know of? CH3, O, CH3, etc. This is what you need on your diene. On the other hand, on your dienophile, the only thing that you need is an electron withdrawing. What is an electron withdrawing group? And very, very popular examples are a carbonyl with the OH, a carbonyl with just an alkyl, but something related to a carbonyl, a cyanide, and so on and so forth. So now if you look back, where is your diene and where is your dienophile? We see that on this alkene, you have a CO CH3 kind of a group. So this is going to be my dienophile, this is going to be my diene, but this is not in cis version. Can it come in a cis version? Yes, yes, it can. So across the single bond, both the double bonds are on same side. And I have substitutions on the 1,4 carbons, making this diene very, very electron releasing. So electron rich diene. You see what these arrows are? Do you all understand what these arrows are? The CH3 groups or alkyl groups attached at this carbon are pumping their electrons into this carbon. They are electron releasing groups. Plus my dienophile. Now, whenever Diels-Alder reactions occur, they occur under heat. So your 1,4 addition reactions will take place. So do you remember we were just looking at this? Whenever you will have a diene and you're heating it up, you are going to get 1,4 addition reactions as your major products. So what is it that we do? We will first make our cyclohexane. We will then label all the substituents on our cyclohexane. Between carbon 2 and carbon 3, I'm going to have my double bond. So this is my double bond. Let's try this. So I've already labeled my starting materials here. 1, 2, 3, 4. 1, 2, 3, 4. And I can start my counting anywhere. 5 and 6. This carbon is 5, this carbon is 6. On the 6th carbon, I have COCH3, or you could just draw this little carbon with the methyl group. On my 4th carbon, I have 2 methyl groups. On my 1st carbon, I have 2 methyl groups. Between my carbon 2 and carbon 3, I will need my double bond. Is there anything else left for me to do? Nope. And my Diels-Alder adduct, or my product of Diels-Alder reaction, is ready. Using the same dyno file, and I wish you all can see these two together. If you look at my dyno file, I drew the exact same dyno file. But what about my diene? If you look closely, my substituents have changed. 1, 2, 3, 4. Instead of having my substituents at 1 and 4, now my substituents are at 2 and 3. Right? So I know where my dyno file is. This is going to be my dyno file's electron withdrawing group. These are my electron donating groups. And when I will do heat, what is the product that I'm going to form? Follow the same pattern. Draw a cyclohexane, label your structure, label your starting materials, and then put all the substituents, then give carbon 2 and carbon 3 a double bond. But my question to you is, between A and B, who is going to do the Diels-Alder faster? Remember what are the important things that you need to have for a diene. Anybody? Anybody wants to offer? Nobody wants to offer? All right, let's look at this again. So both of my dienes can work so that they become cis across 2 and 3. So across 2 and 3, both my dienes are cis. 1, 2, 3, 4. I have a methyl group on 2. I have a methyl group on 3 as well. Right? The only problem that I saw here was the placement of these substituents. So there are these substituents here and these substituents right here. Looking at this, how many on this alkene, how many substitutions do you see? I see 1, 2. What about these two? These are just hydrogens. So this is a di-substituted alkene. Similarly, this is also a di-substituted alkene. These two are just hydrogens. But if you look back here, what kind of alkene is this? Across this alkene, I have 1, 2, 3 substitutions. So this is a tri-substituted alkene. Similarly here, across this alkene, I have 1, 2, 3 substitutions, making this a tri-substituted alkene as well. So between a di-substituted and a tri-substituted alkene, which will be more electron rich? The tri-substituted will be more electron rich. And hence, between these two different dienes with the same dienophile, the more substituted alkenes will go faster than with less substituted alkenes. Any questions on this part? Any questions? Okay. I'm impressed. And you said question number 24, right? All right. So what is the best synthesis for the following ketone? Now, remember you have to start from this very location. And I want one of the things that all of you must remember when you are doing reactions like this, or you are going to make ethers like this, you always need to remember that your final Rx, so either with your carbonyl, oxygenamine, or with your alkyne, the final Rx that you should attack with has to be a primary Rx. And what is a X? Any leaving group that we know of: chlorine, bromine, iodine, OMS, OTF, OTS. It could be any of those, right? So just remember, for alkyne formations and for your ether formations, the final Rx has to be a primary kind. That's when you will get good results. So coming back to this particular structure, you have to start from here and head up here. So what is your synthetic pattern going to be? You have to look at your number of carbons, your functional group transformations. Then you also have to think about your stereochemistry, your regiochemistry, if it is going to be cis trans, if it is going to be rearranged, anti-Markovnikovs, or Markovnikovs, and so on and so forth. So looking at these, I see this part. One, 2, 3, 4, 5. 1, 2, 3, and then I'm missing my 4 and 5. Okay. So I first of all want to add this ethyl group, the 4 and 5, onto this particular molecule, right? So let's try, and I'm going to do it on my page. So looking at these 3 carbons, I need to add something on at this particular carbon. So to add something on to this particular carbon, I need to have a group on it. Now I cannot just ask CH3, CH2 to go ahead and attack here. I cannot do that. This carbon is not electrophilic enough. And so the first step that I would do is I will make it as a oxidize it. Now I want you to be careful. Don't use chromic acid or any of those, because this is going to take your primary alcohol to an extreme carboxylic position. Don't do that. Use the mild oxidizing agent. From a primary alcohol, you will get a aldehyde. So this is what your aim has to be. Not a carboxylic acid, but just an aldehyde. Why? Because you cannot add anything on this carbonyl. It is going to be impossible for this OH to be kicked out. This part is now in resonance. You cannot kick out the OH from this system. It will be very difficult. So instead, form the carbonyl of an aldehyde or a ketone. That's completely fine. So going back, what is my final product? I just need to add ethyl at this location. I can do that by 2 means. I can either take ethyl magnesium halide, or I can do ethyl lithium, okay, followed by acidic solution, followed by acidic solution. In both of these cases, my CH3, CH2, the CH2 here is going to get attacked. Right? In both of these cases, the CH2 part will go and attack. So let's say in our options, what all options do I have? Oh, I still have to make my OH. Okay. So going back at the third location, 1, 2, 3, 4, I have this carbonyl. I will again use an oxidizing agent. What is an oxidizing agent? Which will add oxygens to my carbon. So I can now, because I will form a ketone anyways, I can now use either this or this. I can use either of them. H2CrO4. I can also use PCC. I can now use both of them because this is a secondary alcohol. Now with both of these, I'm going to get, so even if I follow this path or if I follow this path, with either of these reagents, I'm going to get this particular structure. So the first is chromic acid. Can you all see my screen, or are you still seeing the structure? So if you look at this, if I had used this, what would I get? I would have gotten my carboxylic acid, and I don't want that. So A is out of question. None of these are using the oxidizing agent first. So none of these is going to be my product. Now I'm definitely interested in this pathway. If you go back and look at what I had, I also had PCC first. Why? Because you don't want your primary alcohol to become a carboxylic acid all the way. The next thing that I used is a Grignard or a lithium organometallic compound. They are using the Grignards, ethyl, magnesium, bromide. Now my ethyl part will attack here and I will get H, OH, and my ethyl. The last is chromic. Now it will not matter. In my primary alcohols, it will matter, but not in my secondary alcohols. I can use chromic acid. I can use PCC also. So this OH is going to be oxidized and I will get my final product. So I think the answer is B. Is the answer not B, or does this answer your question? Okay, I'm not sure who had asked that question. Oh, I think that student might have left per chance. Oh, okay, okay. All right, very good. Okay, so any other questions? Is the
Oh
answer
no, I think
C?
C is the answer.
C is the answer. Okay. So just be careful in your answer options that you should also try to make your own product first. Try to give them all your particular stereochemistries, the Markovnikov rule and the anti-attack or syn attack or what needs to be done in the mechanism. Then look in the options. Which of these options suit my product the best? Okay, so on your scratch paper, when you will be doing your exam, just draw them out first.